Lecture 19, excuse me, we continue doing a lot. I know it seems like kind of like, I have this image of like a fire hose of information. It's like you have your mouth open and just water coming in so fast. It's like the information coming in so fast. It's hard to take it all in. And that is the downside of trying to fit all of Calculus 1 into one semester. It would be more ideal if it were like a high school course and we can take 2 semesters or something, or at least meet more days per week. But to cover the official content of the course, you do need to do all these topics. I am trying to emphasize lots of different things. I'm trying to emphasize that there's factual information that you should remember, and that's something you should practice for the quizzes and in the gateway. There are concepts you should understand, and then you want to try to tie them together in the big picture, and that involves doing more than just sitting here listening. It also involves then putting into practice with the completion of homework and then the project. In lecture 19a, we are going to start by talking about the project. Part of the project is Newton's method, but that's really a small part of the project, actually. So I'll give you the big picture of the rest of the project. Derivatives of inverse sine and inverse cosine. This really means inverse cosine here as well. Derivatives of inverse functions in general. Then I put more antiderivatives in both A and B because I'm not exactly sure where it's going to fit. Could be in lecture A, could be in lecture B. Then more multivariable calculus, and we're going to tie it to something called implicit differentiation as well. So, what else about project 1? It's mostly about iteration. Iteration of functions in general, not necessarily just with Newton's method, as you are finding out if you've started the project, which I hope you have. By the way, if you didn't find a group, you're going to have to then work on the project on your own. Okay? So I hope you all found groups. The project is in large part about exploring things that can happen when you iterate a function. You use a function over and over and over again is what I mean by that. In other words, when you use the following recursive equation over and over and over again. X sub n equals f of x sub n minus 1, n starting at 1, then going to 2, then going to 3, etc. So that's similar to Newton's method, except it's not exactly the same. Instead of taking x0 minus f of x0 divided by f prime of x0, we just take f of x0 to find x1. Then that number becomes the input for the function, and you apply it again. It's like you take this number and plug it back into the function to get a new number, x2. Then you take that number and plug it back into the function again to get yet another new number, x3, etc. You could do that infinitely often, okay? In theory. The idea is what happens to these iterates. What is the orbit, so to speak, of these points along a line or in a picture of the cobweb plot type that is in the project. You also see in the project a discussion about fixed points. Not every point is a fixed point. In fact, it's pretty rare that a point will be a fixed point. They are where the input equals out the output. If you start at x0 and find x1, x1 equals x0. And then x2 equals x1, and x3 equals x2, etc. They're all the same. That's called a fixed point. Algebraically, to find the fixed points, you've got to solve this equation, f of x equals x. Where does the input equal the output? Typically, that occurs at maybe 1 or 2 spots. For our typical kinds of examples, at least. It can occur more, but for our typical examples, it occurs at maybe 1 or 2 spots. You've got to solve that equation. If f of x were quadratic, for example, as does come up in the project, you'd solve this equation. You could use the quadratic formula, though you'd want to subtract x from both sides first. Right? You want to get 0 on one side before using the quadratic formula. That's something extra you can do as you're working through your project to try to find fixed points besides just experimenting with the cobweb. Attracting fixed points are, first of all, fixed points, not just any point. They are fixed points that attract the iterates of nearby points. In other words, numbers. If A is an attracting fixed point, and if x0 is sufficiently close to A, then xn approaches A as n goes to infinity. The points get closer and closer to A. You could imagine it on a number line. If A is right here, and it's an attracting fixed point, maybe x0 is right there, x1 is right there, x2 is right there, etc. They could be getting closer and closer to A. They will be, in fact, if A is attracting and if x0 is closer to A. It's possible for them to oscillate back and forth below and above A. This could be x1, then this could be x2, then this could be x3, then this could be x4. It's definitely possible to have an oscillation there. It still would be attractive. On the other hand, repelling fixed points don't attract nearby points, they repel them. If x0 is sufficiently close to A, then the numbers xn move farther away from A as it increases. It's repelling if, when you start close to the point, how close is close? Well, you kind of just got to experiment. If you start even arbitrarily close to the A, the point moves away as you keep iterating. That would be repelling. But these things are fixed points. They first have to satisfy this equation. And the cobweb plots are just meant to help you understand this visually, understand the iteration visually. They are not the exact same picture as Newton's method. It's a similar kind of thing, but definitely not exactly the same. And the fixed points occur where the graph of your function crosses the graph of this line, the 45-degree line through the origin. Where those cross each other, that's where the fixed points are going to be. And so that can help you visually see where the fixed points are going to be, as long as you pick your window correctly. So let's do an example. I will come back to the slide. Also put in our shared folder. Well, this is the example from the handout, or the electronic handout for your project. This cobweb plot is kind of similar to the Newton plot, but it doesn't give you the exact same graph. This is the example from the reading. The function is cosine of x. I can apply the cobweb plot and see what's happening. What is the syntax? The syntax is the first thing that goes there is the function name, after this case. This is telling you the x window that you want. This is telling you the y window that you want. I could change those. I could click -1 to 3 here for the x window if I wanted to, and it would change the window. Right? Now x is going between -1 and 3. This is the seed. That's x0, which I took to be 0.1. And then this is the number of iterations, 5. Start at 0.1. You can see the numbers here. The next value, x1 is 0.995. Then x2 is this. Then x3 is this. Then x4 is that. Then x5 is that. 5 iterations. I could have done more. I could have done 50 iterations. Don't do that with the Newton plot because, again, it stalls. But with this cobweb plot, it can definitely be done. And look, it seems like the numbers settle down toward some specific number here. That number is approximately one of the fixed points. It's where the red and blue lines, the red curve and the blue line cross, right there. And the spiraling that you see reflects the fact that those numbers up there are oscillating. Bigger, smaller, bigger, smaller, bigger, smaller, once they get close to 0.739. What's going on in this picture? Well, the initial condition, the c, x0 is 0.1. That's the first and second coordinates of this point on that blue line. I go straight up to the red graph, up in this case because the red graph's higher than the blue line. The second coordinate of that point is x1. Look at x1 this right up here. It's 0.995. Where's x2? Well, go sideways to the blue line where y equals x. This point has coordinates 0.995, 0.995. Plugging 0.995 into the cosine, you can see gives you about 0.544499. That's the second coordinate of that point. I got to go down to the graph in this case because it's below the blue line. Second coordinate's about 0.55 there. I guess closer to 0.54. Keep doing this process of going sideways to the blue line and up or down to the red curve. And you are forced to spiral in toward the fixed point here. This would be an attracting fixed point. Of a spiral in nature. You can try other functions here. I could try cosine of, say, 2x. Oh, my goodness, what in the world is happening there? Let's make the y range a bit bigger. Whoa, what in the world? Something weird is happening. Some weird things will happen in your project too. What would you say about this? You would say, well, it's definitely not settling down on any particular number. This sequence of numbers has no limit in this case. You could say it's chaotic. You could describe it with that kind of word. weird things can happen sometimes. Okay? There's still just one fixed point where the red curve crosses the blue line. It's still pretty close to 0.74, I believe. If I start with a C of about 0.74, well, actually this one would not be, sorry. Let me just try to estimate where it is visually. Oh, maybe it's close to 0.5. One's about there, yeah, 0.5 is pretty close. You can see it spiraling away from that fixed point. Evidently, the fixed point is close to 0.5, but the number is getting further away from it. That must be a repelling fixed point. Where is it more precisely? You could use n-solve to find it out. N-solve, where is cosine of 2x equal to x? That's the kind of syntax you want to use with double equal signs. It can't do it because it's trying to do it symbolically. Here's a different way to do it. Find root. And give it an initial guess. This is kind of like estimating the root on your calculator. The fixed point with this example, cosine of 2x, is pretty close to 0.514933. I plug in 0.514, say, I'm pretty close to the fixed point. I still move away from it. It still spirals away from it first, and then it does wild things. Okay. So that's a very quick summary of some real important points from the project. Take those things to heart as you work in the project. Okay? As you think about it this week. There's still going to be a lot of completion assignment problems to do for Monday as well. So again, don't procrastinate. Okay? Do some today. Work on some today. Can I clarify anything there? Again, those extra videos will help too. I've got more examples in those, so I encourage you to watch those too. Oh, I thought I animated this to make that graph come up last, but evidently not. What's the derivative of inverse sine, also known as arcsine? We can use the same method as we had on Wednesday. Assuming its differentiability, we're not proving it's differentiable. So we're kind of cheating in a sense, but it's still worth doing. Use the definition of the inverse sine, that equation right there, to derive the answer. Okay, I got the graph up here already. Here's the inverse sine graph. It's a reflection of the sine graph across the line y equals x, but only a piece of it. Its inputs must be between -1 and 1. Its outputs must be between -pi/2 and +pi/2. It's about 1.57, plus or minus 1.57. That equation is true as long as x is between -1 and 1. Differentiate both sides, assuming differentiability. Just like we did for the log and the inverse tangent. On the right side, the derivative of x is just 1. That's nice and simple. On the left side, we don't know what that is, but we can use the chain rule to rewrite it a bit. The outside function is the sine function, and I know its derivative is cosine. The derivative of then the sine is cosine. Plug in the inside function, multiply times the derivative of the inside function. And this now allows you to solve for this derivative algebraically, instead of with limits, or instead of with infinitesimals. Just divide both sides by cosine of the inverse sine of x, like that. So that is the derivative of inverse sine, but evidently, according to this picture, it's got a simpler formula. Secant of inverse sine of x is that fraction right there. Why? You can again draw a right triangle to help you figure it out. The right triangle you draw is not a proof, but it helps you get the right answer. Draw a right triangle. Label one of the other angles with the symbol, in this case, inverse sine of x. And you could call that theta if you want, but you don't need to. You can think of the outputs of inverse trig functions as angles if it's useful to think that way. And this is an example where it's useful. Then you got to think about SOHCAHTOA. By the way, every time I'm doing right triangle trigonometry, I always have to remind myself of SOHCAHTOA. It's just so easy to forget otherwise. That sine, for example, is opposite over hypotenuse. I spelled it wrong. Don't spell it wrong. Opposite over hypotenuse. SOHCAHTOA. What is the sine of this angle? The sine of this angle is x. By definition of inverse sine, sine is also opposite over a hypotenuse. This leg over the hypotenuse, that ratio evidently has to equal x. So you might as well take that to be x and that to be 1. It's not the only choice. You can pick this to be 2x and this to be 2, this to be 3x and this to be 3, this to be 4x and this to be 4. Doesn't matter, that's the simplest thing to pick. From the Pythagorean Theorem, this side is going to have length square root of 1 minus x squared. Why? Because, well, if you called it y to begin with, say y, the Pythagorean Theorem would say x squared plus y squared equals 1 squared. Solve that for y by subtracting x squared from both sides and then take the positive square root. You get that. It's got to be positive because it's a length. What's the cosine of this angle? Cosine is adjacent over hypotenuse. There's the adjacent side. There's the hypotenuse. This is square root of 1 minus x squared. So the secant of that angle is the reciprocal of the sine. It's 1 over square root of 1 minus x squared. Because the secant is defined to be 1 over cosine. And you can see looking at the graphs that it seems about right. There's the final answer. Little technicality. While this equation is true when x is between -1 and 1, including the endpoints, this equation is true only if you do not include the endpoints. You'd be dividing by 0 if you plugged in plus or minus 1 for x there. You can't divide by 0. What's happening graphically is the slope of the tangent is approaching infinity as you approach 1 from the left, or as you approach -1 from the right. In a sense, the slope at the endpoints is infinite. Is a visual way to see why you can't plug in plus or minus 1 for x there. We can do the same thing for inverse cosine. I'll go quicker. In fact, you don't even have to write this down. Maybe just write down the final answer. Well, let's look at it quick. Same kind of derivation. This is the definition of inverse cosine. Differentiate both sides. The right-hand side differentiates to 1. On the left side, use the chain rule. The derivative of cosine is negative sine. But you got to plug in the inside function and multiply times the derivative of the inside function. That's the chain rule there. Now just solve for that derivative by dividing both sides by this. Get a negative sign on the right. Cosecant of this angle turns out to be that. Here's something interesting. Coming back to the same picture here. If this angle is labeled inverse sine of x, this angle would be inverse cosine of x. Cosine of that angle would be adjacent over hypotenuse, still x. So sine of this angle would be opposite over hypotenuse, this over this. Cosecant is 1 over sine. So I can say that. And this, and I can ultimately write that. Hey, isn't that interesting? That's the same as the derivative of inverse sine, except for the minus sign there. Weird. Is that true? Yes, it is. And that also means, interestingly, if you take the derivative of the sum of inverse cosine and inverse sine, which once more I remind you could also be written like this, arccosine plus arcsine, and you could see it that way on the gateway. The derivative by linearity would be negative 1 over the square root plus 1 over the square root, which is always equal to 0 for all x in the domain here where it works. Interesting. The sum of the inverse cosine and inverse sine has a derivative always equal to 0. What's that? The graph of this is, yeah, it's horizontal. It's got to be constant. But it doesn't look constant, does it? I'll leave it to you to graph that in your calculator and see it's a constant function. This graph is a horizontal line. So it's technically undefined between negative 1 and 1. The derivative is 0, the function must be constant. Horizontal graph. Slope is always 0. Over the particular domain where that derivative is 0. Here's derivatives of inverse functions in general. This is real important for the completion assignment due Monday. I can mimic the exact same process in general. Give me an arbitrary invertible function f, whose inverse function is f inverse. There's the defining equation for f inverse. It satisfies that equation. It undoes f for all x in the appropriate domain, which I'm not specifying here. Once again, differentiate both sides. Get this. The right-hand side once again differentiates to 1. Once again, you can use the chain rule on the left-hand side and write the left-hand side that way. Think about it. Don't just write it down. Think as you write. I have just used the chain rule on the left-hand side to take the derivative of this. I have an inside function and an outside function. The chain rule says take the derivative of the outside function. There it is, f prime. Plug in the inside function. Then multiply times the derivative of the inside function. And this is the derivative we'd now like to solve for, just like we did with these other examples. So divide both sides by f prime of f inverse of x. And get that formula there. That's a formula that's true then in general, as long as appropriate conditions are made about the differentiability of f and f inverse. We're not worrying about the technicalities of how to prove this exactly. This is more of a derivation. It's good enough for us. It is kind of a confusing equation, though. That confusion can be helped by considering an example. Here's our example. I picked a cubic on purpose to make the inverse function difficult to solve for. Theoretically, if you solve for the inverse function of this, it is possible to find, but it involves a real complicated formula. So you would not want to solve for it. You would not want to find a formula for the inverse function. But you still might like to know the derivative of the inverse function at a certain point, perhaps. For example, you might want to know what is that derivative. And I've used a couple different notations here. The derivative with respect to x of the inverse function evaluated at x equals 3. Or you could use prime notation, f inverse prime of 3. I claim it's possible to find this derivative without finding a formula for f inverse. Let's think about it a little bit here. Go ahead and write it this way. What is f inverse prime of 3? In other words, what is the derivative of f inverse at 3? What's its rate of change at the input equal to 3? According to this formula, it's 1 over the derivative of the original function evaluated at f inverse of 3. Well, the derivative of the original function is certainly easy to find out. The original function is x cubed plus x plus 1. That means its derivative is 3x squared plus 1. But what's this number? How in the world can I find f inverse of 3 when I don't have a formula for f inverse? Well, I purposely picked an example that can be done. This cannot always be done so easily. It can maybe be done approximately sometimes. I purposely picked an input for F inverse that's possible to find by either guessing or by looking at a graph. Notice that f of 1 equals 3. When you plug 1 into f, you get 3. Therefore, never told you this, by the way, 3 dots like that means therefore. Like a triangle with 3 dots. It's a shorthand for therefore. Therefore, f inverse of 3 is what? 1. Right? They undo each other. If f maps 1 to 3, f inverse has to map 3 back to 1. If f of 1 is 3, f inverse of 3 will be 1. Let's switch it. Now we can then plug this in. Well, plug it in here quickly. Oh, no, sorry. Go ahead and plug it in here. F inverse of 3 is 1. So now I need to do 1 over f prime 1. 1 over 3 times 1 squared plus 1 is 1/4. The answer is 1/4. 0.25. Here's what the picture looks like. The blue graph is f. That's the cubic. X cubed plus x plus 1. It looks like your general cubic that's got a positive coefficients for x cubed. They either look like this or like this. It does have a slope equal to 1 when x is 0, which is the coefficient of x. That happens to be the case. And its vertical intercept is 1, right there. Notice f of 1 is 3. This point has coordinates 1, 3. The slope of its tangent line is 4. F prime of 1 is 4. Focus on the bottoms of those fractions. Visually, if I graph the inverse function as a function of x, its graph will be the reflection across the 45-degree line through the origin. It'll be this red graph. To see the symmetry, turn your head this way, the 45-degree angle. Oh, now it looks nice and symmetric. The blue and red graphs are reflections of each other. So it should make sense intuitively that these slopes are reflections, the tangent lines are reflections of each other. And what that means ultimately is when you multiply those slopes, you're going to get 1. 1/4 is the slope, such that when you multiply by 4, you get 1. It's kind of like their slopes have to average out to the slope of this line, which is 1. That's what's going on visually. Okay? So this is one of the trickiest parts of the completion assignment you're going to do. Let's do the antiderivatives and then we'll take the quiz. Here's some more examples of antiderivatives. Indefinite integrals. Those two phrases, antiderivative and indefinite integrals, are synonyms. They mean the same thing. Although, sometimes when you use the word antiderivative, you're just talking about one particular function, not necessarily with a plus c. Always, when you write indefinite integrals, you put the plus c in the answer. You always do that. What's that indefinite integral? What's the answer? I hope you can say it pretty much within a couple seconds. Sine of x plus c. Why? Because the derivative of any function, sine of x plus c, is cosine of x. The derivative of sine of x is cosine of x. The derivative of c is 0. C is constant. Integral of sine is negative cosine of x. It's a little tricky. We know the derivative of sine of x is cosine of x. That's why the first integral antiderivative is true. We know the derivative of cosine of x is negative sine of x. That does mean the derivative of negative cosine of x, by linearity, you can essentially bring the negative sign out, is negative of the derivative of cosine of x. The opposite of it, if you prefer using the word opposite instead of negative. The reason some teachers use the word opposite instead of negative is because this doesn't have to be a negative number, but it has the opposite sign of whatever the sign this has. That's why they use the word opposite. But the derivative of cosine of x is the opposite of sine of x. These two negative signs cancel, giving you sine x. So that is linearity of the derivative, so it tells you you can bring that negative sign out in front. And that last fact is why this thing here is true. This one looks really hard, but if you've got a certain derivative fact memorized, it's actually easy. Does anybody know the answer? Tangent of x plus c, because the derivative of tangent of x is secant squared x, or 1 over cos squared x. Either of these, those are the same function, so either is okay. Therefore, the integral of either of these functions is tangent of x plus c. Calling these things indefinite integrals, does that mean there are definite integrals as well? The answer is yes, but we're not going to get there until a month or so from now. That one looks hard, but it's actually easy. It's inverse tangent of x, or arctangent of x, because the derivative of that function is that function. So even though these things look hard, they are actually easy if you understand the concepts clearly. Not that all integrals are easy. There are plenty that are hard, if not impossible, to do. I will show you some examples of that later. When I say the word impossible, I mean it's impossible to find a simple formula for the answer. It doesn't mean there isn't some function that is an antiderivative. It's just there's no simple formula for it. And this one looks hard, but it's easy. By the way, you also could write this last one as negative inverse cosine of x plus c. Though if you did that, technically the c would be different than the c because there's vertical shifts from each other. I think after the quiz, I'll show you why in graph. Okay, let's stop the lecture and we'll take the quiz.